For almost 50 years, two of our most distant messengers have been sailing through the silent, unending darkness of space. They're little more than machines, bundles of wire, sensors, and fading power sources, but they're also our eyes and hands, reaching out into the great unknown. NASA's Voyager 1 and Voyager 2 were built for a grand tour of the gas giants, Jupiter and Saturn, designed to give us our first real look at these colossal worlds. But then, something remarkable happened. They just kept going. Their paths, by a happy accident of celestial mechanics, carried them far beyond the outermost planets, toward a region no human-made object had ever touched. They were heading for the true edge of our solar system, that invisible boundary where the sun's influence finally surrenders to the vast ocean of interstellar space. What they found there has shocked scientists, redrawn our maps of the cosmos, and handed us a stunning, fiery puzzle that challenges our very understanding of how the universe works. Hook. After a journey of over 40 years, traveling farther than any human object in history, the Voyager spacecraft reached the edge of our solar system. But they didn't find the cold, quiet void everyone expected. Instead, they hit a superheated wall of plasma, burning at up to 90,000 degrees Fahrenheit. The discovery was a shock. It defied our models of space and presented a terrifying question. How could a tiny, unshielded probe from the 1970s survive a wall of fire hotter than the surface of our own sun? The answer isn't just a neat piece of trivia. It forces us to rethink everything we thought we knew about the protective bubble we live in and how it shields us from the harsh realities of the galaxy. To really get the scale of this, we have to go back in time, back to the 1970s. The space race was in full swing, we just walked on the moon, and our gaze was already turning outward to the giants of the outer solar system, Jupiter, Saturn, Uranus, and Neptune. For centuries, they had been just faint dots of light in our telescopes. Then, a once-in-a-lifetime opportunity popped up. A rare alignment of these planets, something that only happens once every 176 years, meant a single spacecraft could visit all four, using the gravity of each planet to slingshot its way to the next. This was the Grand Tour. It was an audacious plan, a cosmic game of billiards that needed incredible precision and a spacecraft built to last. And so the Voyager program was born. Two identical probes, Voyager 1 and Voyager 2. They were wonders of their time, packed with scientific instruments. But they were also incredibly limited. Your smartphone has about 3 million times more memory. They were robotic pioneers, sent on a one-way trip with only the tools they carried and the laws of physics to guide them. In the late summer of 1977, they launched. Voyager 2 went first, followed by Voyager 1 on a faster track. Their mission? Explore Jupiter and Saturn. What came after was anyone's guess. And wow, did they explore. At Jupiter, they sent back the first stunning close-up images of the Great Red Spot, a storm bigger than Earth itself. They discovered faint new rings and, incredibly, active volcanoes erupting on its moon, Io, the first we'd ever seen anywhere but Earth. They saw the icy cracks on Europa, giving us the first hints of a vast hidden ocean. Then on to Saturn. The probes danced through its magnificent rings, revealing strange gaps and shepherd moons we never knew existed. Voyager 1 peered through the orange smog of Titan, Saturn's largest moon, and found evidence of liquid on its surface. It was a waterfall of discovery, but here their paths split. Voyager 1's flyby of Titan flung it up and out of the plane where the planets orbit. Its planetary mission was over. Voyager 2, however, kept going, becoming the first and only spacecraft to ever visit Uranus and Neptune. It found new moons, new rings, and bizarre wind-swept weather. On January 1, 1990, NASA officially renamed the program the Voyager Interstellar Mission. The goal was no longer to look at planets, but to push deeper into the dark, to find the edge of the sun's kingdom. They were heading for the heliopause, a place that, until then, was pure theory. Before we follow Voyager into that uncharted territory, we have to ask, what even is the edge of the solar system? Most of us picture a line drawn after Neptune or Pluto. Beyond that, empty space. But the reality is way more interesting. The sun's influence stretches far, far beyond the planets. Our star is constantly blasting out a stream of charged particles, protons and electrons, in all directions at over 1,000,000 miles per hour. This is the solar wind. This solar wind inflates a giant protective bubble around our entire solar system called the heliosphere. It's a vast, invisible cocoon that acts as our cosmic shield. A shield against what? Against the interstellar medium, the mix of gas, dust, and radiation that fills the space between stars. This medium is full of high-energy particles called galactic cosmic rays, which are incredibly dangerous to life. Our heliosphere is what keeps most of them out. Think of it like the bow of a ship. As our solar system moves through the galaxy, the heliosphere pushes against the interstellar medium, creating a boundary. This boundary isn't a simple line, it's a whole region with multiple layers. The first layer Voyager hit is the termination shock. This is where the solar wind suddenly slows down as it starts to feel the pressure from outside. Voyager 1 crossed this back in 2004. Beyond that is a chaotic region called the heliosheath. Here, the solar wind gets hot, dense, and turbulent. Some scientists call it a sea of magnetic bubbles, like the foamy part of a jacuzzi. And finally, at the very edge of it all, is the heliopause. This is the ultimate boundary, where the pressure from our solar wind perfectly balances the pressure of the interstellar wind. It is the true edge of the sun's domain, where the solar system ends and interstellar space begins. For decades, this whole structure was just a theory. And then Voyager 1 showed up to touch it. The trip through the heliosheath was bizarre. For years, Voyager 1 flew through this cosmic froth. Then, in the summer of 2012, the data started to change, big time. First, the instruments detected a huge spike in galactic cosmic rays, the particles from outside our solar system. At the same time, the particles from our own sun hitting the probe practically vanished. The environment was transforming. The team, led by mission legend Ed Stone, didn't pop the champagne just yet. They were looking for 3 key signs to confirm the crossing: a drop in solar particles, a surge in cosmic rays, and a shift in the direction of the magnetic field. Over the next few months, the first 2 signs appeared with a bang. On August 25, 2012, the readings became undeniable. Solar particles dropped by a factor of 1,000. Cosmic rays shot through the roof. It was like a shield had just been lowered, letting the galaxy flood in. But there was a puzzle. The magnetic field's direction hadn't changed. It got stronger, but it was still pointed the same way. This didn't fit the models. Had it really crossed? The debate was on. The final clue, the smoking gun, came from a solar flare that had erupted from the sun months earlier. This wave of energy finally reached Voyager 1 in April 2013. As it washed over the probe, it made the surrounding plasma ring like a bell. By listening to those vibrations, scientists could calculate the density of the plasma. And it was astonishing, 80 times denser than anything inside the heliosphere. This was the final, irrefutable piece of evidence. It was official. Sometime in August 2012, at over 11 billion miles from Earth, Voyager 1 had slipped into interstellar space. It was the first thing humanity had ever sent to the stars. But the biggest shock was still to come. Voyager 1's data was amazing, but it was just one snapshot in one location. To really understand this boundary, scientists needed Voyager 2. The 2 probes were on totally different paths. Voyager 1 went up and over the solar system, while Voyager 2 was heading down and out through the side. Comparing their crossings would give us a 3D picture of our solar bubble. Was it a perfect sphere, or was it squashed and warped? For 6 years, we waited. Finally, on November 5, 2018, it happened. Just like its twin, Voyager 2 saw the solar particles disappear and the cosmic rays pour in. It had crossed the heliopause, about 119 AU from the Sun. This was a huge confirmation. But the details were even more revealing. Voyager 2 crossed at a slightly different distance than Voyager 1. And that tiny difference? It told scientists something huge. The heliosphere isn't static. It breathes, expanding and contracting with the Sun's 11-year activity cycle. The boundary moves. Crucially, Voyager 2 had a working plasma science instrument. Voyager 1's had failed back in 2007. This meant Voyager 2 could directly measure the temperature and density of the plasma as it crossed. The picture it painted was much sharper. It confirmed the plasma outside is denser and colder than the plasma in the hot, foamy helios sheath just inside. It also revealed the boundary is a bit leaky. Voyager 2 saw a trickle of particles from inside our solar system slipping out into the galaxy. The edge isn't a perfect wall, but something more porous and complex. With 2 successful crossings, the picture was getting clearer. But it was Voyager 2's direct measurements that helped confirm the most mind-bending discovery of all, the wall of fire. Right at the boundary where the solar wind hits the interstellar wind, things get intense. Voyager's instruments registered the temperature of the plasma there, and the numbers were just unbelievable, between 50,000 and 90,000 degrees Fahrenheit. For context, the surface of our Sun is about 10,000 degrees. This is the wall of fire, a boundary at the edge of our solar system hotter than the Sun. So the great paradox is, why didn't the Voyager probes, made with 1970s tech, melt? Why weren't they vaporized? The solution to the puzzle lies in the difference between 2 words we often use to mean the same thing: heat and temperature. Temperature just measures how fast particles are moving. The particles at the heliopause are moving at insane speeds, which is why they have such a high temperature. Heat, on the other hand, is about the transfer of energy. And for energy to transfer, those fast-moving particles have to actually hit you. This is where density comes in. The plasma at the heliopause, while incredibly hot, is also incredibly empty. The density is fantastically low. We're talking about a vacuum more perfect than anything we can make on Earth. Think of it this way. You can stick your hand in a 400-degree oven, but you'll get burned badly because billions of hot air molecules are hitting your skin, transferring a ton of energy. But if a single tiny spark from a bonfire, which can be thousands of degrees, lands on you, you barely feel it. It doesn't have enough mass to transfer any real heat. The wall of fire is like an entire universe of those single sparks. The particles are super energetic, high temperature, but they are so spread out, low density, that they barely ever bumped into the spacecraft. There just weren't enough collisions to transfer any meaningful energy. So Voyager didn't feel the fire because, practically speaking, there was nothing there to feel. It survived because the terrifying wall of fire is actually a near-perfect vacuum. The universe is just full of these mind-bending puzzles, from the edge of our solar system to the heart of a black hole. The story of Voyager is a perfect example of what happens when we get curious. If you love exploring these cosmic mysteries as much as I do, make sure you subscribe and hit the notification bell. You won't want to miss where we're going next. Solving the wall of fire paradox was huge, but what Voyager found has even deeper meaning for us back on Earth. The probes gave us our first real proof of how much the heliosphere protects us. Scientists always theorized that the heliosphere was a shield against galactic cosmic rays. Voyager proved it. As soon as it crossed the heliopause, the level of high-energy radiation shot up, confirming that our solar bubble blocks around 70% of the deadliest radiation from the galaxy. This shielding is absolutely essential for life on Earth. Without it, our planet would be a much more hostile place. This has real practical consequences for the future of space travel. One of the biggest dangers for astronauts on long missions to the Moon or Mars is that very same cosmic radiation. Voyager's data is helping us build better models to protect future explorers. But, as always in science, Answers just lead to more questions. The biggest new mystery is the magnetic field. Everyone expected the Sun's magnetic field and the galaxy's magnetic field to be jumbled up where they meet. Instead, both Voyager probes found the fields were almost perfectly aligned. This suggests a much smoother, more connected boundary than anyone predicted, a kind of magnetic highway letting particles flow between our solar system and the galaxy. We've also learned that the probes aren't in the true interstellar medium yet. They're still in a transitional zone, an area still subtly influenced by the Sun's presence. To solve these new puzzles, NASA launched the Interstellar Mapping and Acceleration Probe, or IMAP, in 2025. It will give us a global map of the heliosphere that the two tiny Voyager probes can't. The Voyager mission transformed itself from a planetary tour guide into an interstellar pathfinder. The fact these two machines, built with 1970s computers, have survived for almost 50 years is an engineering miracle. Their nuclear power sources are fading. Year by year, engineers are forced to shut down instruments to save power. Sometime in the next decade, they will fall silent forever, but their journey won't end. Long after their last message reaches Earth, a trip that now takes nearly a full day, the Voyager probes will keep coasting through the Milky Way. They are our silent ambassadors, our first emissaries to the stars. Fixed to the side of each one is a golden record. It's a time capsule, a message in a bottle thrown into the cosmic ocean. It holds images of life on Earth, sounds of wind and rain, greetings in 55 languages, and music from Bach to Chuck Berry. It's a picture of us. It'll be 40,000 years before Voyager 1 comes anywhere close to another star. The chances of the records ever being found are basically zero, but that was never the point. The golden record, like the Voyager mission itself, is a symbol of our hope, our curiosity, and our need to reach out. The probes drift farther into the great silent expanse, carrying a piece of all of us. And before the end of 2026, Voyager 1 will hit another poetic milestone when it becomes one light day away from home. They are a testament to what we can do when we dare to look past the horizon, to the very edge of our place in the cosmos and beyond. Their journey is far from over, and in a way, ours has just begun.